Today we're going to talk about CMOS transistors, and these transistors are the building blocks for digital circuits. So we'll start with the high-level view, and then we'll dive into the different types of transistors. There are two types of transistors, NMOS and PMOS transistors, and gates. So for example, an AND gate, a NAND gate, a NOT gate. Those gates are made from a combination of both types of transistors, NMOS and PMOS. These gates, called CMOS gates, have both pull-up and pull-down networks. The pull-up network is made of PMOS transistors. So the pull-up network is a PMOS network, and the pull-down network is made of NMOS transistors. So the pull-down network is an NMOS network. And that is always the case for any type of gate that we are going to work with. So let's talk about the high-level view of transistors. So as I said, logic gates are built from transistors, and a transistor is a three-ported voltage-controlled switch. So a transistor is basically a switch. It has three ports or connections. So here's a picture of the transistor with one connection there, the D port, another connection, and another connection. So it's called a voltage-controlled switch because depending on the voltage at the gate, the other two terminals are either connected or not connected. So here's a switch, and when G is equal to 0, so the voltage on the gate is 0, then the other two terminals are not connected. On the other hand, when G is equal to 1, well, now this switch closes, and we now get a connection between the other two terminals, which we call D and S. So these two terminals are called D and S. So again, the high-level view is that a transistor is a voltage-controlled switch. If the voltage on the gate is 0, then the switch, the other two terminals are not connected. The switch is off. On the other hand, if the gate is 1, for example, 5 volts or 3.3 volts, whatever our high voltage is, if the gate is 1, then the other two terminals, in fact, are connected, and the switch is called on. So we have the high-level representation of what occurs depending on the voltage of the gate. And then we also have this symbol for our transistor that shows the three terminals, the gate and the D and S terminals, which are shorthand for the drain and the source. Robert Noyce, who was nicknamed the mayor of Silicon Valley because he co-founded Fairchild Semiconductor as well as Intel, he co-invented the transistor and the integrated circuit. Transistors are built from silicon, which is a semiconductor. It's called a semiconductor because sometimes it conducts and sometimes it doesn't. So in its natural state, a silicon lattice is a non-conductor. It does not conduct because it has few or very few free charges. So silicon is a type 4 atom. Each silicon atom has 4 electrons in its outer shell, and we want to have 8, and so they create bonds between neighboring silicon atoms, so they share that outer electron, and they effectively each then have 8 electrons in their outer shell, and that's a very strong bond. They don't want to give up their electron that's in their outer shell to conduct electricity. So a silicon lattice does not conduct. However, if we dope the silicon with other kinds of atoms, then they can become conductors because then there will be free charges available to conduct electricity or conduct current. Here's an example of a doped silicon lattice. So we get these atoms in there either by diffusion or bombarding the silicon lattice with these other atoms. So in this case, we have arsenic. Arsenic is a type 5 atom. So that means it has 5 electrons in its outer shell. So 4 of those electrons bond with its neighboring silicon atoms. And then a 5th electron does not form a bond with the neighboring silicon atoms and floats around. That leaves the arsenic atom positively charged, so it becomes a positive ion. And this negative, importantly, this is the most important part, this negative charge, this electron is now free to float around the lattice and conduct electricity. So this is called an N-type. N stands for negative because negative charges or electrons are floating around. So N-type means negative. Okay, so we have this N-type silicon. We can also have P-type. So here's a boron atom that we've doped this silicon lattice with. So boron is a type 3 atom. And so boron forms bonds with 3 of its neighboring silicon atoms. But then it wants to form a 4th bond, but it's lacking. It only has 3 electrons in its outer shell. And so it steals an electron from one of these bonds and becomes negatively charged and creates that fourth bond with the neighboring silicon atom. So boron is now a negative ion. And somewhere out here, there's now a missing, for example, here, a missing bond, and it's wanting to be filled with a negative charge or an electron. So really this, quote, positive charge here, this one right here, this positive charge, is really not a positive charge. It's really a lack of an electron. But we call that a positive charge or a hole. And so P-type, the type of charges that are able to conduct electricity or conduct current, are positive charges or really a lack of an electron. So this is called a P-type silicon or P-type doped silicon. Okay, so we have these 2 types of silicon, and now we're going to create a transistor using both of these types of silicon. So here's a picture of our MOS transistor, or metal oxide silicon transistor. And so we've taken, so if you look on, top down looking at a chip, there's some chip, and we lay out a bunch of things, and we have, a transistor here and a transistor here, and really there are millions or even billions of transistors. But what we've done is we've taken a slice through this transistor and we've turned it on its side, and this is what we're looking at. So we're looking at this slice of a transistor. So really this transistor goes right in 3D. It goes out this way. Okay, so the way that we build this transistor is first we take some silicon, it's P-type silicon, it's called the substrate, and then we have these N-type diffusions. Don't worry about that word too much. We have these N-type areas here on either side, separated by this P-type substrate. And then we take this, basically this sandwich of, this gate connects to, used to be metal, so we'll call that metal. Now it's polysilicon, which is basically a very good conductor. It's just easier to integrate into the process of making transistors, but effectively think of it as metal. It's a conductor. And then we have silicon dioxide here right below it. So here's some silicon dioxide. And silicon dioxide is basically glass or an insulator. So it's an insulator, and it keeps charges from flowing from one side of it to the other. But if we take this, we have basically this metal oxide And then we have a semiconductor, a P-type substrate. So we have a conductor, an insulator, and another conductor, semiconductor, P-doped silicon. And that looks a lot like a capacitor. So if you've seen that before, great. If you haven't, now you know this is what a capacitor looks like. A capacitor basically has a conductor, two conductors separated by an insulator. So here's our conductor, here's another conductor. And so if we put positive charges on one side of this conductor, what happens is negative charges then collect on the other side of the conductor. But they can't pass through because of the insulator between them. So here we have, again, this metal oxide silicon sandwich here in the middle. And if we, in fact, dump positive charges on this gate, say we charge it up to 5 volts, or the high voltage, what happens is on the other side of the insulator, the silicon dioxide, we have negative charges that are attracted because of the electric field. So because we've dumped positive charges there, negative charges are attracted on the other side of the insulator. Really, they want to get to those positive charges and neutralize them, but they're stopped because of the insulator. And so we notice that, hey, we just said that in this N-type silicon, there are a bunch of free negative charges. Now we have negative charges here in this, what's called the channel, and a bunch of negative charges here. So now we have this connection through the channel from the source to the drain. So again, if we charge up our gate to VDD, or 5 volts, for example, remember VDD is the high voltage in our system. So if we charge that up to 5 volts, we dump charges, then positive charges onto the gate. Because of the electric field, negative charges are attracted to the other side of the insulator, and it creates a channel and a connection between the source and the drain. On the other hand, if we tie our gate to ground, well, here we tie our gate to ground, and we have our substrate is always tied to ground. And now we have two sides of a capacitor that are at the same voltage. And so now no charges are accumulated here. And now there's no connection between our source and our drain. And remember, it goes back to our picture here. When the gate is 0, there's now no connection between the source and the drain. However, when the gate is 1, we have that channel, and the source and drain are connected. So again, when the gate is 0, we say that the NMOS transistor is off because there's no connection between the source and the drain. However, when the gate is 1, we say that the transistor is on because there is a connection between the source and the drain. PMOS transistors are similar to NMOS transistors, but they work in the opposite way. So a PMOS transistor is on, or in other words, the source and drain are connected when the gate is 0. A PMOS transistor is off, or in other words, the source and drain are not connected when the gate is 1. And we make this, so physically, this transistor is made by having PMOS diffusions, that's why they're called, or P-type diffusions, that's why they're called PMOS transistors. And then, again, we still have our gate, which is metal, or currently polysilicon, but basically a conductor, separated by silicon dioxide, or insulator. And so when we dump negative charges, tie it to 0, right? Tie our gate to ground, to 0. Now, our substrate for PMOS transistors is tied high to VDD. Remember, that's our VDD symbol. And so if we tie our gate low to ground, now positive charges will be attracted to the other side of the insulator, creating a channel between the source and the drain. So again, when the gate is 0, that's when this transistor turns on. When the gate is 1, however, well, now we tie our gate to high to 1. Our substrate again is tied to 1 as well. Now there's no voltage across this capacitor here, this metal oxide, or conductor, oxide conductor sandwich. And so now there are no charges attracted on the other side of the gate. And so there's no connection between the source and the drain. So this physical understanding of how transistors work is important because it's not just magic. We can understand at a lower level how these transistors work. That said, I will never ask you to draw a transistor at the silicon level. It's important for you to understand it. I won't ask you to draw it. I do, however, expect you to understand it at this high level. So the high level is, well, here's the symbol for our NMOS transistor. It has our 3 terminals, the gate, the drain, and the source. An NMOS transistor is off when the gate is 0. So there's no connection between D and S when the gate is 0. And the NMOS transistor is on when the gate is 1. In other words, D and S are connected when the gate is 1. PMOS transistors are the opposite. And that is indicated by this bubble, this inversion bubble on its gate. So for a PMOS transistor, it is on, or S and D are connected, when its gate is 0. And again, that's emphasized by the bubble on its gate, the inversion bubble. A PMOS transistor, on the other hand, is off when its gate is 1. Okay, so now let's talk about how we build CMOS gates, so NOT gates, NOR gates, NAND gates, etc., using these transistors. So we're always going to have a pull-up network and a pull-down network for every single gate. Let me say that again. Every single gate will have both a pull-up and a pull-down network. The pull-up is always made from PMOS transistors. Let me say that one more time. The pull-up network is always, always, always made from PMOS transistors. The pull-down network is always made from NMOS transistors. So here's an overall picture of what our gate's going to look like. Again, we're going to go through some examples and then come back to this slide because this is an overview picture. Kind of makes sense. It will make more sense once we do some examples. But again, our gate has its inputs and outputs. So if we drew a black box around this, we wouldn't necessarily be able to tell the difference between this and, if this is what we're drawing and that. We have inputs and outputs. But now we're going to build it at a lower level of abstraction. Why do NMOS transistors belong only in the pull-down network? Well, the pull-down network is going to pull our output down to ground. So pull down gives us a path to ground. The pull-up network gives us a path to VDD, or pulls the output high, pulls it up to 1. The reason we only have NMOS transistors in the pull-down network is because they pass good zeros. PMOS transistors, on the other hand, do not pass good zeros. However, conversely, PMOS transistors pass good ones, and so they belong in our pull-up network. So again, our pull-up network always consists of PMOS transistors and only PMOS transistors. Our pull-down network, connecting our output to ground, always includes only NMOS transistors. So let's observe how this works. So this is what we talked about a long time ago, that our NOT gate has a name, a symbol, an equation, and truth table. And now we're going to build it at this lower level, at this transistor level. So when A is 0, well, we expect the output to be 1. But let's see if it actually happens in our transistor level gate. So our P1 transistor, or PMOS 1, is, let's see, it has a 0 at its gate. So that means it's on. Or in other words, it's conducting between our other two terminals, our D and S terminals. When A is 0, again, on our NMOS transistor, well, NMOS is off if it has a 0 on its gate. So now we only have a connection between VDD and Y. And so Y, in fact, is pulled up to 1, or to VDD. So now we can observe the other possibility for the input. When A is 1, our PMOS transistor has a 1 on its input, on its gate. And so we know that a PMOS turns off, or its other two terminals are not connected, when its gate is 1. So there's no connection between its two terminals. And we know that an NMOS transistor, if it has a 1 on its gate, it is on. Its other two terminals are connected. And so now we have a connection between Y and ground, and in fact Y is pulled down to 0. So, as expected, when A is 0, Y is 1. When A is 1, Y is 0. And we have effectively created an inverter using transistors. We can also build more complex gates using PMOS and NMOS transistors. Here's an example of a NAND gate. So here we have two PMOS transistors in parallel, and our NMOS transistors here on the bottom are in series. So you'll note that for these more complex gates, whenever our NMOS network is in series, our PMOS network is going to be the complement. It's going to be in parallel. And parallel means, well, there are two paths that could be taken in parallel. Versus in series, this bottom network with our NMOS transistors, these are in series because they come one after the other. So for a series network, so in this case, our NMOS network's in series, it's an AND operation. So they both have to be true in order to get a connection to ground, between Y and ground. So both of those transistors have to be on in order to get a connection. So N1 has to be on for conducting, and because they're in series, N2 has to be on. However, in parallel, it's an OR relationship where P2 has to be on to get a connection between Y and VDD, or P1 has to be on, or both. But the parallel connection indicates an OR relationship. Okay, so let's observe what happens in each of these cases. So if A is 0 and B is 0, so we have this case, A is 0 and B is 0. Well, we have a 0 on P1 and a 0 on P2. So P1 is, it's a PMOS, has a 0 on its gate, and that bubble indicates, a 0 makes it turn on or connect. So P1 is on. And same thing with P2. It has a 0 on its gate. That bubble indicates that it's inversion. So a 0 turns this gate on, and we get a connection between its other two terminals, D and S. So P1 and P2 are on. And so we know that we actually have parallel connections both P1 and P2 connect the output Y to 1. Let's double check and make sure that N1 and N2 are off, or at least one of them has to be off, so that we don't get Y connected to both VDD and ground. That would be contention. But we look at this and we say, okay, let's see, N1 has a 0 on its gate. Yep, and NMOS turns off, not connected, and has a 0 on its gate. N2 also has a 0 on its gate, also is off. There's no connection between Y and ground, and Y is in fact pulled high by the PMOS network. Here, that's the VDD symbol up there at the top. Now we can look at the next case where A is 0 and B is 1. So A is 0 on the P1 gate and B is 1. Well, P1 is on. Remember, PMOS turns on with a 0 on its gate. And P2 is in fact off because it has a 1 on its gate. The NMOS transistors, well, N1 is off because it has a 0 on its gate. And N2 is on because it has a 1 on its gate. So we look at the pull-down network, the NMOS network, and it's cut off. So Y comes down here. That's as far as it gets. It does not have a connection between Y and ground because N1 cuts off that connection. Both N1 and N2 have to be on in order to get a connection to ground. However, for the pull-up network, P1 is on. And so that gives us our connection between VDD and Y. So Y is pulled up to 1 through the pull-up network. And you have to note here that they're complementary as well in that the pull-up network either pulls up the output Y to 1, or the pull-down network pulls the output Y to 0. So one of the networks is going to be activated, either the pull-up network or the pull-down network, but never both. Otherwise, we would get contention on Y, where the pull-up network is trying to pull it up, and the pull-down network is trying to pull it down. So one and only one of the networks, pull-up or pull-down network, is going to be activated at any given time. So now let's look at the next case, where A is 1 and B is 0. Well, symmetry would tell us that it would be a similar result, but we can go ahead and analyze it. So B is 0, so P2 is on. A is 1, so P1 is off. A is 1 again, and so N1 is on. B is 0, so N2 is off. And so our connection between Y and ground is cut off because of N2. But we have a connection between Y and VDD through P2. And so our output Y is pulled high to 1. And now we can look at the last input combination, 1, 1, and see what happens. So if A and B are both 1, we get a 1 on P1's gate and a 1 on P2's gate. So both of those transistors are off because they're P-type transistors. No connection between the D and S terminals on those. And N1 is on because it's an N-type, and it has a 1 on its gate. And N2 is on because it has a 1 on its gate. And so we get the output Y tied to ground. So Y is pulled down to 0. So now we can observe that, yes, in fact, this gate, this transistor level gate, indeed performs the NAND function exactly as we expected. So here it is, nicely written. I also want to show you another way of thinking about this. So We can think about it in two more ways. So if we were asked to build this gate, if you were given, hey, just this, or we already know that, if you were just asked, build a 2-input NAND gate using transistors, well, there are two ways you could go about that. So we have our equation, y equals a and b, all of that bar. That's our NAND function over here. And we can use De Morgan's to turn that and to an or, take down the terms, and invert them. So we get y equals a bar or b bar. So we can build our pull-up network from that. And we can say, okay, cool. This or relationship, here's our or relationship. Remember, or means parallel. Two paths to VDD, or two ways to turn it on, either a bar, that bubble makes it bar, a bar, or b bar. And there's our output y. So now we have our pull-up network, y equals a bar, or, that means parallel, b bar. Remember these bubbles here give us the bar. So if a is low, that gate turns on and connects y to VDD. Or if b is low, this PMOS gate turns on and connects y to VDD. Okay, so we see that we have our PMOS transistors connected in parallel. So that means that our NMOS transistors are going to be complementary, and they'll be connected in series. And they'll be connected to the same inputs as well. So there's another way to think about it. We could also have started with our original equation. So here's method 1. Method 1. And here's method 2. Both work the same. Y equals a and b, all of it bar. So we could complement both sides to get an expression for y bar equals a and b. That means we want y bar to be true when a and b is true. So y bar should be true when a and b are true. Or in other words, y should be 0 when a and b are true. So now we can draw our NMOS. This specifies our NMOS network, or pull-down network. Because we want y to be pulled down to 0 when a and b are true. So and means series. They both have to be true to get a connection. So here we have a and b. Both of those are true. A and b, we're going to get a connection between y and ground. So we start with that, and we have our NMOS, our pull-down network, in series. And so that means that our pull-up network is the complement. The opposite of that, our pull-up network, is in parallel and connected to the same inputs. So you'll see that we ended up with the same circuits either way, but two different ways of thinking about it. Whichever way you prefer sounds good. Okay, so let's now try a different gate. Let's try a 3-input NOR gate. How would we build that using transistors? So let's start by writing the equation of a 3-input NOR gate. Y equals A or B or C, all of that bar. There's our 3-input NOR gate. And so we could let's use a method 2 to start with. So complement both sides, we end up getting y bar equals A or B or C. So that specifies our pull-down network. They're in an OR relationship. So OR means parallel. So we're going to get A or B or C. Pull our output Y down to 0. A or B or C. And because we have our NMOS or our pull-down network in parallel, our pull-up network will be in series. 1, 2, 3. And connected to the same inputs. And so here we have our 3-input NOR gate. We could have also started from here, y equals A or B or C, all that bar, taking De Morgan's on that. Those ORs turn to ANDs, bring down the terms, get A bar and B bar and C bar. So we'd start with our pull-up network, which would be A bar, there's a bubble, and series, B bar, because of the bubble, and C bar, because of the bubble. And then because we had our pull-up, our PMOS in series, our pull-down would be in parallel. So here's our pull-down in parallel because it's the complement of our PMOS network. So again, we ended up with the same thing. Either way, we started either starting with the pull-up or starting with the pull-down. We're going to end up with the same network either way. So here it is, written out nicely for you. We could also, if you were just given this gate, you could figure out that it's a NOR gate by saying, okay, let's see, these are in series, so it's going to be an AND relationship. And we get A, it's coming in here, A bar, series, so it's AND, B is coming here, bubble, B bar, again, series relationship, and C coming here with the bubble, C bar. So we get Y equals A bar and B bar and C bar. We could also read it from the pull-down network and get Y is going to be low, or in other words, Y bar is going to be true when I've connected this one using wires instead of by name. Eventually, even if I connected by name, if I had written, instead of just using that wire, if I had just written A here, in practice, those need to be wired together. There's only one input, A, and I need to wire anything that needs to be driven by A to that wire. But for kind of ease of schematics, you can also connect them by name. But so here we have A. It's in a parallel relationship. These are all in parallel relationships with Y and ground. So Y bar equals, we know it's going to be an OR, A, or B, or C. We take the complement of both those sides, we get Y equals A, or B, or C, all of that bar, which using De Morgan's is A bar and B bar and C bar. So we can read it from either the pull-down or the pull-up network. So now a question is, how do we build a 2-input AND gate? So you might want to pause the video right now and try that on your own. So we can start with the equation, y equals A and B. Well, we could go ahead and implement that using the pull-up network. Y equals A and B. This is the incorrect method, but I'll show you the correct one in a moment. Logically correct, but not the most efficient. So if we want to get an A up there, we know it's an AND relationship. We know AND is series. So that's why I put those PMOS transistors in series. In order to get A out of this transistor, I need to put A bar on its input. And in order to get B out of this transistor, I need to get B bar on its input. So I get B bar bar, which is involution, just B. So Y equals A and B. There's the pull up. And because the PMOS transistors are in series, the NMOS transistors are going to be in parallel. And we're going to get the same inputs, A bar and B bar. And that looks pretty good. We could also double check that this worked. We could read the equation from the pull down network. We get Y bar, Y is going to be low, or Y bar will be true, when A bar, that's this one, or, because they're in a parallel relationship, or B bar is true. Doesn't really look like an AND gate yet, but if we take the complement of both sides, we're going to get involution. Y equals, well, that OR turns into an AND. We bring down the terms, and then we complement each term. Involution again, Y equals A bar bar, which is A, and B bar bar, which is B, and we do in fact get our AND function. Okay, so I said this wasn't quite right. It's close and logically correct. So nothing wrong with this logically. This would function, would look like an AND gate. I can't tell the difference between the more efficient version, which we'll build now. But the thing that's hiding behind this is A bar and B bar aren't free. So we have the true versions of inputs, but in order to get the complement version of our input signals, we need to have inverters. So for this, we would need to have an inverter. Remember, that's what our inverter at the transistor level looks like. An inverter for A to get A bar, and an inverter for B to get B bar. So even though it looked like I used just 4 transistors for this circuit, in fact I used 4 plus 4 transistors, so I actually used 8 transistors for this circuit. So there's actually a more efficient way to build this gate, and in fact it's to build the NAND gate followed by an inverter. So CMOS gates build inverting gates more easily or with fewer transistors than non-inverting gates. So inverting gates use fewer transistors. So at the transistor level, a NAND gate, well, let's see, Y equals A and B, all of that bar. So we could do this, Y bar equals A and B. Here's our NAND gate. I'll call this like Y1 or something. Y1. So our NMOS is in series. So our PMOS will be in parallel. And I'm connecting it by name. So here's our NAND gate. And now we connect that to our inverter. Looks like this. And we get Y. So now instead of 8 transistors, I just need to use 6 transistors. So while they're both logically equivalent, the one that I built on the prior slide, logically equivalent, this is the most efficient way to build an AND gate, is actually to build the NAND gate followed by an inverter. So back to our higher level view of our CMOS gate. A CMOS gate stands for, again, C stands for complementary. Complementary. M stands for metal. Metal. O stands for oxide. And S stands for silicon. So they're complementary because it's using both PMOS and NMOS to build the gate. And metal oxide silicon refers to that metal oxide silicon sandwich of the gate. So our CMOS gates always, always, always have a PMOS pull-up, so a pull-up network that has only PMOS transistors in it. So the only kind of transistors that you'll see in that pull-up network will have bubbles on their gates. And pull-down networks that consist only of NMOS transistors. So any NMOS transistor or any transistor in the pull-down network will not have a bubble on its gate. So they'll all be NMOS transistors. And again, every CMOS gate is composed of both a PMOS pull-up and an NMOS pull-down. Gordon Moore co-founded Intel with Robert Noyce in 1968. And he observed what's called Moore's Law, which is that the number of transistors on a computer chip doubles every year. And he observed this in around 1965. Since 1975, transistor counts have doubled about every 2 years. So here's an example of how Moore's Law has worked. Well, we start with 1970, where the first commercial Intel processor was announced, the 4004. And it had, on the order, you'll notice that these transistors here, this y-axis is logarithmic. And so if we have a linear trend here, and we have a logarithmic scale, it means that it's actually exponential. So we have the years here on the x-axis, and we've plotted the different Intel processors on this graph. And so as we get higher and higher, so, on the order of 3,000 transistors in 1970. So I guess 3,000 still, quite a few transistors. Now we get up to, for example, the Core Duo up here, and we have upwards of 300 million transistors. And we're definitely up in the billion transistors on a chip at this point. And so why is that? Well, the main effect is that the transistor sizes are shrinking. So those gates, everything, all of them, actually all the dimensions are shrinking and getting smaller, so we can fit more transistors on a chip. So a famous quote about computers and really the underlying transistors that build a computer is, if the automobile had followed the same development cycle as the computer, a Rolls Royce would cost about $100 today, get 1 million miles to the gallon, and explode about once a year. So chips really aren't that fragile. This is a bit of a sarcastic comment. But the truth behind this is that the fact that the number of transistors on a chip has grown exponentially, our ability to do more and more complex processing has really enabled most of the technology that we use today.